So we were talking about the inputs of pavement ME. So for what we were left off at the dynamic modulus master curves for mixtures, hot mix asphalt. And now we're going to continue with other inputs, like level 1 super pave inputs for binders, asphalt binders. So if you actually look at this asphalt binder component, you have an input requirement at different temperatures, G star, binder G star, which is the dynamic shear modulus of asphalt, and phase angle at different temperatures. So we use this device that we mentioned yesterday. This is also a close-up view. You can see the G star of the binder ranges from 8 million, 9 million, almost 9 million pascals to 1,000 pascals when you move from 40 Fahrenheit to 168 Fahrenheit. Pretty big difference. So we talked about this yesterday a lot, but today let's also cover this quickly. Now we have the dynamic shear rheometer. This is a device called dynamic shear rheometer. We place a binder sample in between two parallel plates. And these plates, typically in this device, they have a diameter of 25 millimeters. And at high temperatures testing, for intermediate temperature testing, we use 8 millimeter plates, for those of you who weren't here yesterday. And the gap here is 1 millimeter for high temperature testing, and it's 2 millimeters for intermediate temperature testing. So a torque is applied in a cyclic motion, and cyclic torque is applied and cyclic strain is measured, or cyclic strain is applied and cyclic stress is measured, and eventually either one of them. Then what we do is we calculate the parameter G star, which is the peak stress divided by peak strain. I am just checking if everybody's there. Okay. All right. So then we talked about what frequency means. So the frequency is essentially 1 over the delta t. Delta t being, in this case, from peak to peak, the time difference from peak to peak. In this case, 0.1 seconds. 1 divided by 0.1 second is 10 hertz. That's our frequency. And you've seen this yesterday. This is the dynamic shear modulus test being run at different strain levels: 0.1% strain, 4% strain, and 9% strain. So at this level, this is just too large for this temperature. This was a relatively low temperature, intermediate temperature. So that's why we there's a failure of this test actually. You can see the sample split in half because of too much strain. But here, these are good tests, cyclic tests. Now, so from this G star data, there's a curve that's called dynamic modulus master curve. That's what we discussed this morning. Now, the pavement ME software develops this master curve from the input that you input. So, and at the end of the analysis, when you run the pavement ME, if you look at the PDF output, the output of the PDF, you're going to see this. This is a snapshot of output of the pavement ME. And what you're seeing here is you can see in the horizontal axis logarithm of reduced time, vertical axis E star in PSI. Reduced time and reduced frequency, they're interchangeable, except reduced time is 1 over F, 1 over the frequency, or reduced frequency is 1 over T. So it's essentially 1 over this number is the frequency. Here, you can see the numbers are -6, -5, because they are actually in log. This is the logarithm of the time. So this is 10 to the -5, and this is like 1 second, and this is 10 seconds, and 100 seconds, and so on. So now, as I said, the time here, in the definition here is 1 over frequency in this particular condition. And the sigmoid equation, so if you look at the equation, delta plus alpha divided by 1 plus beta plus gamma times logarithm of t sub r. So this is the same equation that we used to develop. So I'm going to go back a few slides, and I'll come back here. So if you go back and look at this slide, when we were talking about development of dynamic modulus master curve, this equation and that equation that you saw are identical, except instead of logarithm of time, we use here logarithm of frequency. So that's the only difference between this equation and that equation. That's why curve looks this way in here, and in Payment-ME it looks the other way. So let's try to understand this curve a little more in depth. So instead of B1, B2, B3, and B4, Payment-ME uses delta, alpha, beta, and gamma. So in the earlier slide that I showed, B1, B2, B3, and B4, Payment-ME uses a different terminology, delta, alpha, beta, and gamma, same thing. And also the difference, logarithm of time, reduced time here. Now, alpha and delta, let's look at what these means in this equation. If you look at the dynamic modulus master curve, delta corresponds to the minimum possible modulus. That's what delta means in that equation, minimum possible modulus. If you actually look at the form of the equation, if the logarithm of t, if the t goes to infinity, to this direction, this becomes infinity. A number divided by infinity is 0, so this component goes to 0. Log E star corresponds to delta. So delta is actually nothing but logarithm of the minimum possible modulus that an asphalt mixture can happen. Okay, that's what the delta means. Delta plus alpha is the maximum possible, and this difference between minimum and maximum is alpha. So that's what this alpha is all about. So when the logarithm of TR, this goes to 0, then this goes to 0, and this is 1. So then this is actually alpha plus delta. So that's maximum, this is minimum. So if you look at this NCHRP 147 report that I mentioned, that tornado plot that I mentioned, there is that HMA alpha parameter, very significant. HMA delta parameter, very significant. That's what those are. So HMA, hot mix asphalt, alpha parameter, hot mix asphalt, delta parameter. Those are the two things. So in that NCHRP project, if you look at that, let's go to those slides really quickly. Where is the tornado plots? Right here. If you look at this, so we were looking at HMA alpha parameter was very significant input. HMA delta parameter was very significant input. So these are essentially the winners in terms of the significance of the inputs on the outputs of the Payment-ME.